Hey, welcome to The Explainer. Think about this for a second. You step into a little metal box, push a button, and without even thinking about it, you trust it to whisk you hundreds of feet into the air. It's something we do every day. But have you ever stopped to wonder what's actually happening on the other side of those doors?
Because it's definitely not just a box on a rope. What's really going on is this incredible symphony of physics and precision engineering. So today, we're going to pull back the curtain on that hidden world, and we'll be using some fantastic insights from the engineering specialist at Noveen Poya Lift to guide us.
Okay, so where do we even begin? Let's start in the heart of the whole system, the machine room. This is where all the raw power comes from, the muscle needed to lift thousands of pounds. And for a hydraulic elevator, it really all comes down to two key things.
First up, you've got pressure. You can think of this as the pure brute force. Engineers have this big job of calculating the absolute maximum weight, the car itself, a full load of people, plus the heavy hydraulic jack, and then figuring out the exact amount of force needed to push all of that up.
But all that force doesn't mean much if you're not moving. And that's where flow rate comes in. This is all about speed. It's how much hydraulic oil gets pumped through the system to get the elevator car going. So more flow means a faster ride. It's pretty simple, really. Pressure is the how much, and flow rate is the how fast.
So, how do you take these two ideas and pick the right electric motor? Well, you start by multiplying the pressure and the flow rate. That gives you the raw power you need. But, no machine is ever 100% perfect. Engineers have to account for the fact that some of that power, maybe 15 to 30%, is just going to get lost to things like friction and heat. Factoring that in is absolutely critical to make sure the motor they choose is truly up to the task.
All right, so we've got the power figured out. Job done, right? Well, not so fast. Because when you apply all that force, you create a brand new problem. You have this long hydraulic jack pushing a super heavy car, and that puts it under enormous stress, which leads to a huge engineering challenge, the risk of buckling.
To really get what this means, just picture trying to push something heavy with a single, long, uncooked spaghetti noodle. What's going to happen? It's going to immediately bend and snap, right? It's useless? Well, that exact same principle applies here. Under all that pressure, a long steel jack actually wants to bow outwards and fail.
The solution, though, is honestly pretty brilliant in its simplicity. They use something called jack guide shoes. These are just simple supports that brace the jack against the guide rails on the wall of the shaft. And that one little addition completely changes the physics. It transforms the jack from what engineers call a weak free column into a super strong multi-supported beam. It's just such an elegant and effective fix for a massive safety problem. Okay, we've talked about all the solid steel parts, but what if I told you that one of the biggest challenges for elevators isn't solid at all? In fact, it's just air. The empty space in the shaft creates these powerful, invisible forces, all thanks to something called the stack effect.
So, in the winter, you can think of the entire elevator shaft as one giant chimney running right through the middle of the building. All the warm, cozy air inside is less dense, so it naturally wants to rise. This creates a powerful updraft, causing high pressure up on the top floors and low pressure down at the bottom. It's literally pulling air up through the whole building.
And in the summer, you guessed it, the whole thing flips. Now the cool, air-conditioned air inside is denser than the hot air outside, so it sinks down the shaft. This creates a downdraft. And this is actually something you might have noticed. Ever heard a weird whistling sound in a tall building or felt a door was strangely hard to open? That could totally be the stack effect at work.
Speaking of doors, let's talk about the one part of the elevator we all interact with. We probably don't think about them much, do we? They just open and close. But that smooth, reliable motion is no accident. It's actually a carefully engineered dance of forces.
That little door motor is working way harder and smarter than you'd think. First, it gives a big initial shove, maximum force to get that heavy door moving from a standstill. Then, it almost immediately backs way off, just using a tiny bit of power to let the door glide open smoothly. And then, right at the end, it actually applies force in the opposite direction. It hits the brakes to give you that soft, quiet close.
And that brings us to our final stop, inside the car itself. Because everything we've talked about so far, the power, the stability, the doors, it all exists for one reason: to make sure that what you, the passenger, experience is both incredibly safe and totally comfortable.
Now, when we talk about a comfortable ride, It's not actually about speed or even acceleration. It's about how smoothly the acceleration changes. You know that feeling when a car or a train suddenly lurches forward. That feeling has a name. Engineers call it jerk. And that jarring, lurching feeling is precisely what safety standards are designed to limit, making sure every ride feels perfectly smooth.
And just how strict are those standards? Well, during a normal ride, the forces you feel are kept to a really gentle push. But the system is built for the unexpected. In a full-blown emergency stop, it's designed to handle an acceleration of 9.8 meters per second squared, which, you might recognize, is exactly the force of gravity. This ensures that even in a worst-case scenario, the forces are well within safe, survivable limits.
So, the next time you step into an elevator, just take a moment to think about the symphony that's happening all around you. It's so much more than a box. It's this perfect harmony of raw power, structural genius, invisible air forces, and precision control, all working together seamlessly just for you. And that really makes you think, doesn't it? From the car you drive to the washing machine in your house, what other everyday objects are hiding this incredible level of engineering complexity? The world is just full of these hidden symphonies, working perfectly in the background if you just know where to look.